In this video, we're going to talk about how to solve systems of linear equations by the graphing method. So here is, remember that example that we were looking at earlier. We had these two equations, x minus y equals 2 and y equals negative 2x plus 7. The first equation, we found a bunch of solutions. Now, if we plotted the points that corresponded to those solutions, 2, 0, and 3, 1, and 4, 2, and 5, 3, and 0, negative 2, and negative 1, negative 3, and so on, those would all line up. So the graph of that equation is the straight line that includes all of those points. And in the second equation, y equals negative 2x plus 7, has a graph that looks like this. So all the points on this line have coordinates that work in that equation. We have 0, 7, way up here somewhere. We have 1, 5, and 2, 3, and 3, 1, and 4, negative 1, and 1.3, 4.4, and so on. And do you see the point where these two lines cross? The point that's on both lines, not just one or the other? Right there at 3, 1. The point where the x-coordinate is 3 and the y-coordinate is 1. So that would be the solution to the system. So here's the procedure for solving a system of equations by graphing. First, carefully draw the graph of the first equation, as explained in Chapter 3. Then, carefully draw the graph of the second equation on the same set of axes. I say carefully because you need the points all in the exact right place so that you will be able to see where the two lines that you come up with cross, if they do. So when you draw these graphs, you should be doing it on graph paper so you can get a nice accurate graph. And you need to be careful to make sure the points that you draw are in the right places. So you have a nice accurate graph. Then, once you've got both lines drawn, look for the point where those two lines cross and find the coordinates, the x and y coordinates of that point. That should be the solution to your system. But you ought to test those coordinates in both equations. If they work, you've got your solution. And if they don't work in both equations, then you made a mistake somewhere. Somewhere in your graphing or in your testing or somewhere. Now, occasionally, you're going to get two lines that don't cross. In that case, the system has no solution. And in that case, we say the solution is inconsistent. Another thing that could happen is that the graphs of the two equations turn out to be the exact same line. And in that case, we say the system is dependent. Instead of just having one particular point that works in both equations, any point on that whole long line is going to work in both equations. So you have infinitely many solutions. So the most common situation is where you just have one solution, because you have two lines that cross at just one point. But you can also have two lines that don't cross at all, and you can have two lines that are right on top of one another. They're really the same line. And if they are straight lines, those are the only possibilities. You can't have two straight lines that cross at two different points, but no others. So now that we know what we're doing, let's work through some examples. Let's solve this system by the graphing method. X minus 2y equals 2 and 4x minus 4y equals 12. So we start by drawing the graph of the first equation. And to draw the graph of an equation, we need to find two or more pairs of numbers that work in the equation and then plot those points and draw the line through them. And you can find any pair of numbers that works. You can pick a number for one of the variables and plug it in and solve to see what the other one is. And you can do that with any numbers, but often an easy number to work with is 0. Don't underestimate 0. 0 is a nice, easy number to work with. So let's see what happens if I take this equation and I put 0 in for x. If x is 0, what does y have to be to go along with that? So we're looking at 0 minus 2y equals 2, which would just mean that negative 2y equals 2. Divide both sides of that by negative 2, and we get y equals negative 1. So 0, negative 1, the point where x is 0 and y is negative 1, is one solution to that equation. So I'm going to go ahead and plot that point. Now let's see what happens if I put 0 in for y. X minus 2 times 0 equals 2. Well, 2 times 0 would be 0, so we're just looking at x minus 0 equals 2, or just x equals 2. So there's the point where x is 2 and y is 0, the point 2, 0. So that would be there. And if you want to find a third point just to make sure that they all line up and you haven't made a mistake somewhere, you can. But as long as you haven't made any mistakes so far, we know exactly where the line has to go. It has to go through those 2 points. So there it is. That's the graph of the first equation. Now it's time to graph the second equation. 4x minus 4y equals 12. So let's see what happens if I put 0 in for x. 4 times 0 minus 4y equals 12. So negative 4y equals 12. Divide both sides by negative 4, and we get y equals negative 3. So one pair of numbers that works in that equation is 0, negative 3. The point where x is 0 and y is negative 3. Now we have to find another pair of numbers that works. Let's see what happens if I put 0 in for y. 4 times x minus 4 times 0 equals 12. Well, 4 times 0 is just 0, and 4x minus 0 would just be 4x. So if 4x equals 12, we can divide both sides of that by 4 and get x equals 3. So we've got the point 3, 0, the point where x is 3 and y is 0. And now that we have these 2 points, we can draw the line that goes through them. Now that we've got our 2 lines drawn, look at the graph and find the point where they cross. Can you see it? What are the coordinates of that point of intersection? The coordinates of this point are 4, 1. We're over 4 in the x direction and up 1 in the y direction. So it looks like the solution to this system is 4, 1. Let's check. If we put 4 in for x and 1 in for y, the first equation says 4 minus 2 times 1 equals 2. That's true. And the second equation says 4 times 4 minus 4 times 1 equals 12. Well, that would be 16 minus 4, and yes, that is equal to 12. So that's true. So we have our solution. Let's try another example. X equals 2y plus 2 is the first equation, and 3x minus 6y equals 12 is the second equation. So take the first equation and find a couple of points so that we can draw the line. I put in 0 for x, and then solving for y gives me y equals negative 1. So there's the point 0, negative 1. And then if I put 0 in for y, I get x equals 2. So there's the point 2, 0, and there's my first line. For the second equation, 3x minus 6y equals 12, I could put 0 in for x, and I get y equals negative 2. I could put 0 in for y, and I get x equals 4. So we've got a line that goes through the points 0, negative 2, and 4, 0. And now that we have these 2 lines, where do they cross? What's the point that they have in common? Well, they don't cross. They don't have any points in common. So that means that this system here has no solution. There's no way to get both of these equations to be true at the same time. There's no pair of numbers that works in both equations. So we would say the system is inconsistent. Okay, what about this system? X equals 2y plus 2 and 3x minus 6y equals 6 are the two equations in this system. So, first equation, we've done this before. The graph is the line through 0, -1, and 2, 0. It looks like this. The second equation, if x is 0, y has to be -1. And if y is 0, x has to be 2. So that's the very same line, the exact same line, passing through 0, -1, and 2, 0. Since it's the same line for both equations, any point on that line is going to work in both equations. They're both true when x is 2 and y is 0. They're both true when x is 0 and y is -1. They'd both be true when x is 4 and y is +1, or when x is 6 and y is 2, or anywhere along this line. We have infinitely many possible solutions. Now, that doesn't mean anything goes. A point that's not on the line isn't going to work in either one of the equations. But as long as you have a point that works in one of them, it's also going to work in the other one. So there's infinitely many solutions, and we would say that this system is dependent. What about this system? Here I've already got the graph drawn for you. The orange line is the graph of the equation 4x plus 3y equals 7. And the green line is the graph of x plus 2y equals 3. From looking at that graph, can you tell what the solution to the system would have to be? Did you say 1, 1? Because there's the point where the lines cross, and that point has x equal to 1 and y equal to 1. And if we check that in the equations, 4 times 1 plus 3 times 1 does equal 7, and 1 plus 2 times 1 does equal 3. What about this system? Here, the orange line is, or I guess it's red maybe, it's 4x plus 3y equals 7 still. But now the second equation, the graph is this blue line, x plus 2y equals 9. Can you see where these two lines cross? Well, I can see where it is, but the coordinates of that point, I can't tell exactly what they are. They don't cross right at one of the nice integer coordinates. Looks like the x coordinate is somewhere between -2 and -3, and the y coordinate is somewhere between 5 and 6. So that's approximately -2 point something and then 5 point something. So here we see one of the problems with this graphing method. If the solution doesn't come out to be a nice whole number, it can be hard to see exactly what it is. Let me kind of cheat and get a little help on this. I've pulled up the Desmos graphing calculator. It's an app you can get for your phone, and it's also online. You can point your web browser to desmos.com/calculator. I'm going to type in these two equations. 4x plus 3y equals 7. And then x plus 2y equals 9. And that's what we were looking at. There's the point where the lines cross. And when I point to that point, it shows me the coordinates, -2.6 and 5.8. So that's the point where the lines cross. And if you check, that really does work in both of these equations. They're both true when x is -2.6 and y is 5.8.